In part one of this video lecture, we talked about how to do some of the background and electron configurations. And what we'll start to do now in this lecture is learn how to write an electron configuration. All right, so let's start writing some electron configurations. Again, this is the shorthand notation to describe all of the electrons in an atom or ion. And so our rules for writing them is we first have to figure out how many electrons are present. And then we start by filling the lowest energy orbitals and working our way up. So every orbital can hold 2 electrons, but if it has 2 electrons, we would call them opposite spin. So we'd say one is one spin up and one is spin down. Okay, so let's take the simplest example, hydrogen. So hydrogen has 1 electron. So we want to start with the lowest energy orbital, and that energy orbital would be the 1s orbital, and so that's where this electron would go, to the 1s orbital. So its electron configuration would then be 1s1. And you can see in this symbol that 1 refers to the principal quantum number. So we're in the first shell. The s refers to the shape of that orbital, and then this superscript 1 refers to how many orbitals are in that subshell. We could draw what's known as an orbital energy diagram. And if we look at that orbital energy diagram, we can see we have energy. We've labeled our orbital 1s with a horizontal line, and we put an arrow going up or an arrow going down to show that there's 1 electron present. So we can continue and now try helium and lithium. And so if we look at our periodic table, helium has 2 electrons. And so the electron configurations would be 1s2. We've now filled the first shell of 1s orbital. And so the orbital energy diagram would have 1 electron going up, 1 electron going down. Again, that's due to the Pauli exclusion principle. Lithium has 3 electrons. So we'd start in the same place, and we'd still have 1s2, but we have another electron, would go to the next lowest orbital. So 1s2, this shell is full. So now we go to the second shell. So down here at the second shell, 2s1. And if we were to draw that out, we'd show the 1s, and then above it, the 2s, with a single electron in it. So we can look at a couple more examples, and we'll switch here, and let's look together, and let's try boron and carbon. And so I'm going to write these out, and the first thing I would have us do, when you have boron and carbon, is I would find these on our periodic table. So boron and carbon are located here on the periodic table. So boron has 5 electrons, so we might jot that down and say 5 electrons. And carbon has 6 electrons. So whenever we write the electron configuration, we're always going to start at the lowest energy orbital, so that's always 1s. We'll put the first 2 electrons there, so 1s2, and then 2s2. And we can see we're now, when we look at the boron, we are now in the p block. We filled the s, and now we're in the p. So we now have our 2p1. Similarly with carbon, it's going to be the same thing as boron with 1 more electron. So we have 1s2, 2s2, 2p2. Now we can come down and write our orbital energy diagram. I'm going to draw a horizontal line for the 1s, the 2s, and now remember when we go to the 2p, there's actually 3 different 2p orbitals. So I'm going to draw 3 lines. Now I'm going to fill in with my orbitals. I can say 1s has 2 electrons, the 2s has 2 electrons, and there's 1 electron in the 2p. Doesn't matter which of those 2p's you use. Now we can come over here for carbon. Again, we have a similar diagram, 1s, 2s, with one important difference. So the 1s is full, the 2s is full, but now we want to think about this 2p2, and it turns out the lowest energy solution to this is to put those electrons in different p orbitals with the same spin. So I'm going to put them both spin up in different orbitals will give us the lowest possible energy. So we'll try a couple more. And what we'll do is do neon and sodium. So the first thing we might want to do is find neon and sodium on the periodic table. So here's my periodic table. I'm going to circle neon for us, and I'll circle sodium for us. And we'll start off and say, how many electrons does each have? So neon, we can see, has 10 electrons. So we're going to need to account for 10 electrons. And sodium's going to have 11 electrons. All right. So what we want to now be able to do is to account for all of these. And so we're going to start the same way. We have 10 electrons. So we're going to start off with our S, 1s2, 2s2, and now we have to go to the 2p. And if we're following along, we've filled the 1s. That's full. Now we went to the 2s, and now we're on the 2p. We want to go all the way to neon. And we can see the 2p shell will be full when it gets to neon. So that's 1, 2, 3, 4, 5, 6. So we have 2p6. When we now look at sodium, notice we're going to have the exact same thing, but we just have one more electron. And that electron is back in what we call the S block. Right? So this whole first two groups on the periodic table are the S block. So we're going to have the same electron configuration with one more electron. So we have 1s2, 2s2, 2p6, 3s1. And so one of the things I want to draw your attention to when we look at this is that neon, being a noble gas, the last group on the periodic table, right, represents a full shell. So that first and second shell are completely full. And so that 1s2, 2s2, 2p6, right, sodium starts off exactly the same. Right? And then we have one electron in the next shell. We're going to be able to use that to our advantage in a second when we talk about valence and core to start writing an even shorter version of our electron configurations. And so we'll come back to this example in a second. If we come back here, we can start talking about valence versus core electrons. And valence electrons are responsible for chemical reactivity. And the reason it's so important to understand the difference in the type of electrons is when we think about chemical reactivity, all of reactivity is determined by valence electrons. The core electrons are the electrons closest to the nucleus, and they don't typically react because the force of attraction with them is too strong for those core electrons to react. So it's the valence electrons that undergo reactions. When we understand the difference between valence and core, we're going to say that the valence electrons will be those with the highest principal quantum number. So when we look at neon versus sodium, sodium has one valence electron. It's the electrons in the third shell. Right? That's the highest principal quantum number. Whereas in neon, we're going to say has 8 valence electrons because the highest principal quantum number is 2 and the highest shell is 2. And so all the electrons in that second shell will be the valence electrons of sodium. So when we think about writing, we can write right now a condensed or noble gas notation. And when we write this notation, this is going to be a way of summarizing all of the core electrons as a noble gas. And then we can focus on just the valence electrons of an atom. And so the way we would do this is say, if we look at sodium, our core electrons, 1s2, 2s2, 2p6, are really summarized by neon, the previous noble gas. So if we want to write the electron configuration of sodium, the noble gas way of doing it is we say sodium, colon, and then in brackets, neon. And that neon in brackets really is the same as writing the full 1s2, 2s2, 2p6, and then after that, all we have to write is the valence electrons, 3s1. So take a minute and try to write out the noble gas electron configurations of these 4 elements, and then we'll go through them quickly together. So please pause the video and try these out. Okay, so let's go through these quickly together. So you should have noble gas configurations of these 4 elements. So if we look at them quickly, we can say aluminum. So here's aluminum on our periodic table. And so if we look at aluminum, we would want to then start off by writing the previous noble gas. So the previous noble gas for aluminum is neon. So we'd put neon in brackets. And then after we put neon in brackets, we're going to say what is aluminum. So aluminum would be 3s2, 2p1. So we say 3s2, 3p1. We can do the same thing for our titanium. So here's titanium. So the previous noble gas to titanium would go up on the periodic table. We can say the previous noble gas then will be argon. So again, now we'll say argon. And then we're starting the 4th shell, so 4s2. And now notice now we're in the D block, 3d2. Next is francium. So if we look for francium on the periodic table, it turns out to be way down here. And so if we look at francium, this is where the noble gas really saves us. So our noble gas is radon. So we can say radon in brackets, and then 7s1. And finally, we can quickly do palladium. So palladium is located in here in the D block. And so again, if we go up a row, we say the previous noble gas is krypton. So krypton in brackets. And then we just have to start on the 5th row, 5s2. And now we're in the D block, but we have to go down to the 4d. And now if we count across 1, 2, 3, 4, 5, 6, 7, 8 d electrons. And there's your noble gas electron configurations for those 4 elements. Thank you.